In this video, we'll discuss a new allocation method called Jefferson's Method. This method is much stronger than Hamilton's method, but also has a major flaw, which we'll talk about at the end. So let's just go through it with this example. Here I have a table of information, and we have states A through E, and their populations are listed below in the thousands. So if we were using Hamilton's method right now, what we would do is take their total population, 26,000, divide by the number of seats, which is 200, and we would get 130 as the standard divisor. Then what we would do is we would take each state's population and divide by the standard divisor to get each state's standard quotient, or SQ. And we would get those here. We would take the lower quotas and adding them up, that's 198, which means we have two seats that are in surplus. So the first would go to this one because it has a 0.69 residue, which is the highest. The next one would be actually a tie between these two because they have the second highest with 0.46, so we'd have to use some kind of tiebreaker. But the crux of Hamilton's method is that we have surplus seats, and therein lies the problem. We need to figure out how to deal them out to the states. And apparently using just these residues is not a very good idea, as we saw with the paradoxes. So what this new method, Jefferson's method, does is just eliminates surplus seats altogether. It says, well, we don't want surplus seats. What if these lower quotas just added up to 200, which is what we see the final result of Jefferson's method. And how we get that, we have to do a little bit of different math. So here we had the standard divisor was 130, but Jefferson's method said, what if we have a different divisor? So it's often called MD or just D. So MD is modified divisor, or D is just divisor, to distinguish it from SD, which is the standard divisor. So this divisor is not standard, but it achieves a different purpose. So the standard divisor was used to tell us how many people are represented by each seat. But that's just kind of an arbitrary number. We said 130 people per seat. What if we wanted, we could just easily have said 150 people seat, or we can say 100 people are represented per seat, and then we just give out seats depending on that information. The main point here is that this divisor number is not set in stone. We can kind of play with it a little bit. We were just using 130 because it was the more natural thing to do, but we could have just easily used different numbers. So that's the point of Jefferson's method. We want to find a divisor that's close to 130, but it's a little bit different to achieve a different purpose. So, for example, let's pretend we use the divisor as 129, which is one lower than 130. What's that going to do? If you took 5,000 and divided by 129, you're dividing by a smaller number, which means these quotas are going to go up. And that's exactly what Jefferson's method wants. We want these quotas to go up. And in fact, we want this 38 to become a 39 ideally, because that would mean that instead of 198, we would be at 199. And then maybe we'd want to decrease the quota. We want to decrease the divisor even more so that maybe this 46 became a 47. And then we were at exactly 200, and then we wouldn't have any surplus seats at all. So the one thing about Jefferson's method is that we do have to kind of play with the divisor because there's no set way to there's no formula for the divisor. We kind of have to play with it. So, for example, what I did was I took this 130, I did exactly that. I went down to 129 because I wanted these numbers to go up, and I found that when I did that, I got 199, which was not enough. So then I recalculated and I said, okay, I'm gonna have to make my divisor even lower. So I put it as 128, and it turned out that that was just the sweet spot to get 200. If I went higher than that, I would get over 200, and I would have too many seats being given out when there's only 200 seats. So the difficult part of Jefferson's method, if you don't have a computer, then the difficult part is finding this exact divisor, but usually you can kind of you take a guess and then you see what happens, and if this number is too high, then you've made your divisor here too low. You need to get it higher. But if your number here is too low, then your divisor needs to actually go down a little bit. So basically, after playing with it a little bit, you'll find out the correct divisor, and keep in mind this is not the standard divisor. You have to call it MD or just D for modified divisor or just divisor. And then after that, you take the lower quotas, and if you did it correctly, you should have them all add up to exactly 200 because that's the sweet spot you wanted as you adjusted your divisor. And in that case, when you add up these modified quotas, they'll be over 200, but it doesn't really matter because when you take the lower part of each, you'll be cutting off all these decimals and you'll achieve your desired result of just 200. So this kind of avoids the problem with Hamilton's method because it doesn't have to do with taking surplus seats and giving them out in any and dealing with the different ways in how to do that. But here's the major flaw. The flaw is that it can cause upper quota violations, which often favor large states. So an upper quota violation is a violation of the quota rule in the upper direction. So this is a violation where states can get more than their upper quota. And let's just see an example where it can happen. So I'm just going to tamper with this data a little bit just to make a point. So let's say that, for example, this 7.69, when I put 128 or whatever I put, and whenever I put my sweet spot number, my sweet spot divisor, so that all these down here added up to 200, this number right here went up to, let's say, 9.1. Okay, so that means that state C would get 9 points under Jefferson's method. But what's the standard quotient? Remember, the quota rule has to do with standard quotients. The standard quotient is 7.69, which means the lower quotient is 7 and the upper quotient is 8. So the quota rule says that state C should get between 7 and 8 seats, so either 7 or 8. But we see that under Jefferson's method, they got 9. So this is usually going to happen with bigger numbers, but we see that it's possible to happen under Jefferson's method. And this often favors large states simply because this often happens with bigger numbers, so the standard quotas are often going to be bigger when this happens. So just keep that in mind, be wary about that. That is one shortcoming, but it doesn't really compare to the 3 or 4 shortcomings we saw with Hamilton's method.